So, hello everyone. So, we will continue with the measurement of thermal characteristics, and we are discussing the technique guarded hot plate. Guarded hot plate, here we use the technique of directly the thermal transmission measurement by controlling the heat flow from other directions. Okay. And thermal transmission is a reciprocal of thermal resistance, and also we have discussed that the test plate is the main component of this instrument, which is covered by the guarded plates, and the surrounding temperature is kept 36 degree Celsius, that all the plates are kept 33 to 36 degree Celsius, and the surrounding temperature is kept much lower than that. Typically it is around 20 degree Celsius, it is kept. One can keep between 4.5 degree Celsius to 21 degree Celsius depending on the requirement, and the standard relative humidity depending on the requirement, it can vary from 20% to 80% relative humidity. And during the test one has to keep these conditions, atmospheric condition fixed, and one thing one has to take care, this atmospheric temperature should be lower than this skin temperature, so that heat flows out. So, the method is that its sample is placed on the instrument, that is the test plate, and the temperature is allowed to reach its equilibrium, and heat passing through the sample, the specimen is measured in watt per square meter, that is a power consumption by the test plate. And as we know that we have to direct the heat flow through the fabric only. Heat, whatever power is consumed by the test plate, that heat has to pass through the fabric only. For that the arrangement is made. So, here this central plate, it is a test plate, and this one which is around this test plate, it is a guard ring. So, there both test plate and guard ring are made of metallic plate, and they are heated in exactly same temperature. So, if you see, this is the top view, if we see the side view, this central one, it is a test plate, okay, and the guard plate, these are the guard plates. So, the use of guard plate is that, and if we use two separate heater for this, another plate which is a bottom plate, which is at the bottom of this test plate and guard plate, and three separate heaters are there to heat these plates. One heater is for test plate, another heater will be for guard plate, and third heater is for the bottom plate. And the heaters, the power consumption by all the heaters can be noted down, but actual power consumption by the heater, the test plate, the heater which is heating the test plate is used to calculate the thermal transmission characteristics of fabric, and these heaters are plates are heated by the power source, and the temperatures are kept exactly same. So, that the heat flux is not, the heat cannot flow sideway, because the guard ring is of the same temperature, there is no temperature gradient, and it cannot come at the flow through the bottom side, because here the bottom plate is of exactly the same temperature. To restrict the further heat flow, the between the guard ring and the test plate there is another insulation is placed, which is actually cork insulation. So, some insulation material is placed around the test plate, so that it is totally insulated, and the guard ring is also some insulation is placed, so that there is no heat flow. Now, if we heat the material here, so if we heat the test plate, so that heat will flow only upper direction, only through the top, and that and test fabric sample is placed just above the test plate. The heater which is heating the test plate, the power drawn by that heater is used for the heat transmission through the fabric. So, we can directly measure the amount of heat flow through the fabric per unit area, if we know the area of the test plate, and per unit time also. Okay. So, thermal transmission is measured here, which is a reciprocal of thermal resistance. Now, how do we measure? So, thermal transmittance. So, this is the thermal transmittance is also known as U value. In general, it is not only used in textile material, this U value it is used for any other place where thermal transmission is important, like building. So, if we know the thermal transmission of insulating wall or maybe glass window, this U value is used. It is the rate of transfer of heat in watt through 1 square meter of the structure. It may be any structure, maybe textile fabric, okay, structure, divided by the difference in temperature across the structure. Okay. So, that if the in case of fabric, if we know the temperature between the two surfaces, so that the temperature difference is known. So, which is nothing but watts per square meter per Kelvin per unit difference of temperature. So, if we compare the well insulated parts of a building have lower thermal transmittance, like a thick insulating cloth will have lower thermal transmittance than a thin fabric. So, that is why the thermal transmittance is measured. The physical significance of thermal transmittance is this. Now, if phi is the heat transmission in watt, A is the area, U is the thermal transmittance, and T is the temperature difference. So, we can measure the heat transmission if we know the thermal transmittance of the material. Here we are doing in reverse way. In normally we want, if we want to measure the heat transmission in watt, we know the, if we know the thermal transmittance of material like glass window, one insulating wall, if we with a known thermal transmittance, we can, and if we know the area of that wall, or if we know the temperature difference between the two surfaces of the wall, we can measure the heat transfer in terms of wattage. But in guarded hot plate we use the same formula, but here we want to know thermal transmittance of an unknown fabric sample. If we, in that case, we should know the heat, that heat transmission in watt. So, here heat transmission in watt we measure by measuring the heat required by this test plate. So, now let us see the animation. This is a beautiful animation you can see here. Now, this is in case of test plate. Suppose test plate where we do not have any fabric, only test plate, there is no guard plate, there is no bottom plate, there is no fabric. So, what happened to the test plate if we connect the test plate with the heater? Now, let us see, this is the top view and this is side view, and where we are putting only fabric on the test plate and nothing, no guard plate. Heater is attached with that this power source is there, and this is basically nothing but a heater. The test plate is nothing but heater, okay, and power source is there, and here as there is no guard plate. So, heat is being transmitted to all the directions. It gets transmitted through side way, through bottom way, as well as it is transmitted through the fabric also. Now, if we know the power required for this heater, then we cannot say that this power is utilized to transmit heat through only through the fabric. It is a portion of the or fraction of this heat is getting transmitted through the fabric. Suppose it is a x quantity of heat is drawn, power is drawn by this heater, that means a fraction of x will be required to that through the fabric, but we do not know the what is the fraction, that is the problem. That means, this system has to be modified. So, this system is modified in guarded hot plate. So, in guarded hot plate, let us see the animation. So, this is the test plate, this is the front top view, side view, this is the guard ring, okay, guard ring, and here it is a bottom plate, it is placed, fabric is placed here, and now these three plates are connected with the this different power source. Red one is connected with the this test plate, this blue one is the bottom plate, and yellow one is with the guard ring. And now we can see the from red one, red power source, the heat is flowing only through the fabric, in the through the fabric, and no other, it is not going to any other direction. So, that means, whatever heat is flowing through the, it is drawn, the power is drawn by the test plate, that is, if it is known, if it is P, the power drawn by the test plate, and if we know the area of the test plate A and the temperature difference between the test plate, two sides of the test plate, and then in that case we can calculate the U value, that is the thermal transmittance, it is P by A multiplied by T P minus T A. Okay. So, that is how we can measure the thermal transmittance of the fabric. Now, so thermal transmittance of the fabric is we can measure by. So, now coming back to this measurement again. So, this temperature difference if we know, so we can calculate the value of U. So, we can see the typical values of some known material. You can say the single glaze in tight glass. So, it is a 5.7 watt per square meter per Kelvin. So, these are the different. So, well insulated wall, it is a 0.25 watt per square meter per Kelvin. Okay. Well insulated floor, these are the typical value. So, we why are we using this value, why do we want to know this value? Just to get an idea about the standard insulation of standard material, which we regularly come into contact with this type of material. So, triple glazed window allowing for a frame, it is 1.8 watt per square meter per Kelvin. Okay. Now, if we compare these values with our textile material, we can just see that the insulation of this thermal transmittance of this material. So, their thermal transmittance values are very low. So, insulated wall, poorly insulated wall, it is 1.5. So, well insulated one, it is 0.25. So, if we see as compared to this, with the same unit, the fabric material, it is a say thick woven fabric, it gives 20 to 80 watt per square. So, if we have thick woven fabric, the type of insulation we are getting, it is much less. So, very high thermal transmittance. So, we must know this value, then only we can try to develop clothing for some insulation purpose. Thinner woven fabric, it is a 500 to 550 to 200 watt per square meter per Kelvin. Okay. So, these are the different values, and now what we have got. So, combined thermal transmittance is what we get. It is a combined means it is including the air layer. So, it is a U1 is the combined insulation, P is the power loss from the test plate, which that means the power drawn, amount of quantity of power drawn by the test plate. A is the area of the test plate, and TA, Tp and Ta are the temperature of test plate and ambient air. Okay. And then what we have to do to know the transmittance of air, again we have to perform the bare plate test. So, the bare plate test is that it is a, and there for bare plate test we will get the value U2. U2 is calculated the transmittance of fabric. So, UBP is the bare plate, which is actually which shows the air, the thermal transmittance of air. So, effectively finally, if we want to know the thermal transmittance of fabric, so this is the formula 1 by U2 equal to U2 is the thermal transmittance of fabric equal to 1 by U1 minus 1 by UBP. So, using this formula we can measure the calculate the thermal transmittance of fabric itself. Now, another method measurement of thermal transmission characteristics is the Kawabata method, KSF Thermolabo. Okay. It evaluates the thermal transmittance characteristics of fabric, where two plates are used and in between the two plates fabric sample is used. So, the heat plate with a constant temperature of 30 degrees Celsius and cold plate, okay, it is a separate plate with a lower temperature which is standard 20 degrees Celsius, in between the fabric is sandwiched, and then the amount of heat flow is measured, the thermal conductivity is measured in terms of heat flow rate and distance by area and temperature difference. What is the distance? This is the formula, the heat flow rate Q by T, and that heat flow rate from the heated plate. Okay. L is the fabric thickness, that is distance between the two plates, A is the area and delta T is the temperature difference, which is constant here, it is a 10 degree Celsius. So, this using this equation we can calculate the thermal conductivity. So, thermolabo it measures the thermal conductivity, TOG meter measures the thermal resistance, and the guarded hot plate measures the thermal transmittance. Okay. Then coming to another method of measurement of thermal transmission characteristics, it is using the thermal manikin. Thermal manikin, it gives the idea of total thermal transmission of clothing. It is not the in the fabric form, it gives in the clothing form, and it measures the 3-dimensional measurement technique. Heat flows at different direction at different dimensions. Okay. It is used for testing and product development by building and automobile industries. So, that is in there it is used extensively. Also in textile industry it is used for developing clothing with improved thermal properties and performance testing of protective textile. So, for protective textile performance testings, thermal manikin is extremely important, particularly for those applications where it is a hazardous environment, where extremely heat, extreme hot, extreme cold temperature, where normally we cannot perform the subjective assessment. Okay. It is basically it simulates the human body, total human body, and it is divided into many segments, typically 20 to 30 different segments it is divided, and different sensors are placed. Okay. So, number of individually regulated body segments, it is more than 30. Okay, now, so different at different body segments the sensors are placed, where it measures the temperature and heat flow. It can measure the 3-dimensional heat exchange from human body, measures the heat loss due to conduction, convection and radiation. So, the whole body heat loss is determined by summing up the weighted average. So, it at different location we measure the heat loss, and then we measure the total heat loss by weighted average at different, like or depending on the area of that particular zone. So, we can measure. So, here it gives the total heat loss. It can integrate the dry heat loss from the body in a realistic manner. So, it actually that in dry heat loss, and also there is another type of manikin, it is a sweating manikin. So, there it actually simulates the sweat and measures the heat flow. So, here it is a actually realistic manner, means the actual heat flow at different direction, different level it can simulate, and clothing thermal insulation it can measure objectively. So, actual clothing, it is not the fabric sample, here actual clothing it can be measured. So, it is used to evaluate the thermal stress in environment with human body, determine the heat transfer and thermal properties of clothing assembly. So, it is its total clothing assembly, its thermal transmission it can measure, means a number of clothing. It is not only the outer clothing or single layer, it is a different types of clothing including the gloves and shoes also. So, total clothing it measures, inner garment, everything. Prediction of human response to extreme or complex thermal condition, where we normally we cannot go, we cannot perform test, in those conditions thermal manikin is used, like extreme heat or flame in those conditions, and it gives realistic value, and it validates the results from human experiments. So, even it can validate the subjective assessment. So, thermal that mannequin test we have seen. So, it gives the realistic picture. So, after this, now we will discuss the other techniques to measure the thermal protective clothing for extreme heat. So, it extreme heat, and it also measures the flame protection. This is one technique. It is the instrument has been developed here in our lab. So, where the fabric is kept in, the test sample is kept in horizontal position, and here it is a heat sensor, where it is a copper calorimeter sensor, and fabric sensor specimen is there, and this is a burner where direct flame is actually placed, generated, and there is a fabric, there is a blocker, this shutter is there, okay, and shutter is removed manually, but one can do automatic removal also. When shutter is removed, the direct flame is, the fabric is exposed to the direct flame, and the heat flow through the fabric is measured for certain time. And this instrument, we are not interested in the burn characteristics of fabric, we are interested here in the thermal transmission, heat transmission due to the flame, and this calorimeter, the sensor measures the heat transmission, and the temperature increase in that which is sensed by this calorimeter, it is plotted against the time, and which by knowing the rate of increase in time, one can predict the time required for second degree burn, okay, if we compare with the Stolz curve. Okay. So, that way this instrument will give the idea of exposure time of second degree burn. Now, why is it important? So, suppose a person, a firefighter or some anyone who is actually exposed to heat, the particular fabric, how long will it actually be protect the will be able to protect the person from any burn injury. So, there are three types of burn injury I will discuss here. So, this is the experimental setup. Now, let us see the experiment, real experiment. Now, it is adjusting the flame rate, we can adjust the rate of flame, that can be automated also. Now, this is now for now the blocker, that is and it is removed this blocker. Now, with the time the temperature is recorded, and after say 10 second standard time, or maybe we can have 15 second, 20 second, after certain time it is removed, that is the burner is stopped, and we know the temperature rise with the time, and that if we know that with the time and knowing the time. So, we can now predict that particular sample how long one can actually survive in the fire, in case of fire, without any burn injury. So, there are mainly three types of burn injuries. One is first degree burn injury, which is very the low intensity, where it can get recovered quickly. Second degree burn injury is a severe one, but one can actually recover. It is, but third degree burn injury we cannot do anything. So, our this instrument's idea here is to predict the second degree burn injury, because then third degree burn injury means that there is skin, total skin structure is destroyed. Okay. Now, let us see, the burn depth is measured by its severity. Okay. So, first degree burn injury is the skin becomes red, no blister. So, that means that is normally it can get, we can get it covered quickly. But second degree burn injury means, that means it can be recovered, but after a long time, and the person can survive skin blisters, epidermis must be regenerated. So, epidermis, what is the surface, that should be regenerated. Okay. So, that is a type of burn injury, and third degree burn injury means it is a totally, it is a destroyed. So, that means, so our idea here is to know the time required for second degree burn injury, and this one, this is the actually this is a Stolz curve. Okay, here. So, there, and this is the curve which we have actually got from the instrument, this black one, and the point where it is actually intersect with this standard curve, that is the tolerance time. So, that time, if it goes beyond that, that means then your third degree burn injury will start. Okay. And in this instrument, heat flux is actually 4.2 to 16.8, that is the heat flux, and this is the Stolz equation. So, this is the Stolz equation, where T0 is the original temperature of the skin, okay, or test sensor. So, these are the quantitative representation of the skin, that the omega is the quantitative value, okay, and with this value, this is the integral. Okay. This value is the, this is the term integral of the, this omega value, if it is 0.53, it is a first degree burn, okay, and if it is 1, that is second degree burn, in if it is, it takes place in the basal layer, and if it is dermal layer, then it is a third degree burn. So, that way one can get the, it is a thermal integral. And earlier instrument, what we have observed, it is a we have seen that the fabric is in the horizontal direction, but most of the condition, if we talk about our clothing, the fabric layer is in vertical condition. So, it is important to know the what is happening, actually happening in the vertical condition, when the heat source may be radiant heat source or may be flash fire comes from the side. So, this is the fabric layer. Fabric layer typically it is a 3 layer, one is outer layer, that is a middle layer, and the inner layer. So, the outer layer, which is basically it is a protective layer, thermal protective layer, middle layer it is a insulating layer, and this inner layer, which is basically absorbent layer. In case of any sweat and anything, it comes out from the skin. So, it should absorb, and middle layer will actually, it is insulating, it will not allow the heat to flow through that, through the that layer, and outer layer which will actually prevent it from the burning, and also it will act as a reflective layer. So, in outer layer we can have some reflecting layer, so that the maximum heat, radiative heat at least, it should get reflected. Okay. So, and the type of measurement for fire retardant textile or protective clothing, there are different types of parameters one can measure, like ease of ignition. What is that? Means the way, the how quick it get ignited. So, that depending on the type of fiber, type of finished material, we can actually use different types of finishing treatment to change this parameter. Afterglow time is one of the parameters, extent of afterglow, char length is another parameter, flame spread time is another parameter, smoldering time, then limited LOI, limited oxygen index, okay. Heat transmission factor, thermal protection performance TPP test, heat transfer index. Okay. These are the different ways of expression of the fire retardant textiles, but here in this instrument these three parameters will be measured: heat transmission factor, thermal protection performance and heat transfer index. These three parameters quantities can be measured using this new equipment. So, the instrument for here it is a vertical orientation of fabric. Okay. Now, the existing earlier instrument is that it is a horizontal orientation. The most of the other instrument like sweating guarded hot plate, TOG meter. So, all these instruments are the horizontal orientation, but the thermal mannequin is vertical and it is a 3-dimensional, but this instrument it is only vertical orientation which is more realistic. The exposure type earlier we have seen in the video, it is only flame type exposure, but this vertical instrument it is both flame and radiative heat flow and it can work both at a time. Air gap was stationary air gap, there is and in this instrument we can change the air gap, because that to simulate the air that air gap between the skin and the fabric, that is the microclimate thickness. So, and microclimate is not there, that earlier instrument we cannot change the microclimate, but here we can change the microclimate, the humidity of the microclimate we can change. So, at different humidity level the thermal transmission behavior and the exposure which we get, the comfort which we get will be totally different. So, this instrument gives all these advantages over the existing instrument. This is typical view of the instrument. Here this is the source of heat. So, this is the radiative heat source and along with the burner to give the flame. This is fabric holder, fabric sample here is there, and this one is the chamber, the climatic chamber, where we can control the humidity. So, humidity of this is controlled just to simulate our microclimate humidity, and at the back of this here it is the sensor though which will measure sense the temperature and heat flow we can measure, and this is connected with the motor. This is connected with the motor just to control the change the air gap. Air gap is controllable at different air gap. This can be the thermal transmission can be measured, okay, at different level of heat. So, we know it is a radiative heat by flame also. Okay. Now, try to see, this is the flame, it is a flame and here it is a radiative heat source. This is a flame source, this is the radiative heat source. The burner is there for flame and it is a quartz lamp is for radiative heat. We can change the number of lamps to increase or decrease the rate of radiation, radiative heat, and this is the chamber where the fabric is placed here, and fabric holder, this is a fabric assembly, and this is the chamber where we can actually change the humidity of this chamber, okay. And also the depth of this change, that this distance of this chamber is can be changed to change the air gap. Now, this is the air gap which is changeable, as we have seen by motor we can change this distance, and here is the sensor assembly, and sensor assembly is connected with the computer, which directly gets the temperature value, and this is the microclimate chamber where we can actually inject the water vapor or we can draw the water vapor to maintain the humidity level, and humidity level is maintained by actually measured by the humidity sensor. So, at different relative humidity we can measure, we can get the heat, how much temperature, how much heat is flowing, what is the temperature of the skin at the other surface of the fabric, what is the temperature of the microclimate, that we can measure here. Temperature sensor is there, this is the equipment and this is the shutter. So, when we want to measure, start the experiment, we just remove the shutter and we immediately start the experiment. This is the showing the flame, shutter is removed, the heat is flowing, it is flowing through the fabric and ultimately the sensor is receiving the temperature and temperature is increasing and we are getting the plot, okay. And here we can circulate the humidity, we can inject the humidity at different humidity level. So, this is the vertical configuration, more closely to the reality, okay. It is as compared to the benchtop instrument. Wide range of test can be covered by radiant exposure using ISO 6942, ASTM F1939, ASTM F2702. This all these standards can be followed. Flame exposure by ISO 9151, ASTM 4108. So, these standards can be followed and both flame and radiant heat exposure by this standard. So, this is a total, it is a widely it can be used. Dynamic air gap between fabric and skin, microclimate control, it is to control the microclimate humidity, to simulate the sweating. So, the important parameters are effect of type and level of exposure can be measured. So, different level of exposure we can measure, effect of air gap size, effect of dynamic air gap. So, if normally it is very important as far as clothing comfort is concerned when we are in motion. So, at when we move our that air gap keeps on changing, air gaps keeps on changing, so that also it simulates. So, effect of relative humidity, whether we sweat or not, whether we generate humidity. So, that also it can measure, and vertical arrangement. Okay. So, that way it is this instrument gives complete information about the fire protective clothing. So, this is the and this is actual picture. Now, we will discuss the various thermal transmission parameters. Now, till now what we have measured, we have discussed the different measurement technique. Now, we will discuss the different thermal transmission parameters which are practical in nature, and how to correlate with the this practical units with the units which we have got from the instruments. So, the practical unit is like clo. So, that is used for any clothing. So, this all these parameters we will see. So, what is thermal resistance? That we know thermal resistance of textile material is a measure in SI unit in terms of degree Kelvin square meter by watt. It is a basically it is a reciprocal of thermal transmittance, okay, and which we measure in say sweating guarded hot plate. We have seen there we measure watt per square meter per degree Kelvin. Here it is a just reciprocal of that, and R is the thermal resistance of fabric layer. It is actually defined as the ratio of the temperature difference between two phases of the material to the rate of, that is difference between the two phase of the material temperature difference, and to the rate of heat transfer per unit area of the material, that is the rate of heat transfer per unit area of the material, okay, to the phase surface. The practical unit is that it is a TOG. Practical unit of thermal resistance is widely used as a TOG, which is actually 1/10 of the SI unit. So, 1 TOG is 1/10 of square meter degree Kelvin per watt, okay. And another unit is a CLO, which is approximately equal to 1.55 into TOG. So, all this CLO, TOG we will discuss in next session. So, here thermal transmission different parameters will continue. So, till then goodbye, thank you.